the formation of the color, like electron jumps. Then if you want to change the color, if so changing a ligand or changing a coordination number will alter the energy splitting of a d orbital, and that will change the frequency of a light which is absorbed. So we'll not see the frequency of a light which is absorbed. We will observe the one which is not absorbed. So with compound, like there are certain compounds without color, like scandium and zinc. In the beginning, we discussed why scandium and zinc are not considered as a transition element, because scandium, when it loses its free electron, has no, there's no d electrons, or there are no electrons in the d orbital. That is why. So there is no energy transfer equal to that of a visible light. So we don't observe any color. Same thing for zinc and copper 1 as well. Because if you check the copper ion, if you check copper 1, this is copper 2, but if it is copper 1, so there will be one more electron in the d orbital, and d orbital will be filled. So normally copper 1 also does not give us the characteristic color. So compound without color, scandium is a member of D block, and it's a D block element, but we don't say it is a transition element, because the modern definition of transition element, it should have an incomplete d orbital. So it hasn't got any d electron to move, so that's why there is no energy transfer equal to that of visible light, so there is no color. In case of zinc 2 or copper plus 1, the d shell is full, so there is no space for electron to transfer. Like if d shell is filled, like all are having the electrons, so electron cannot transit between the shells. So if electron cannot transit between the shell, we cannot observe any characteristic color. So there is no not an energy transfer equal to that of visible light, because there is no space available for electron to transfer. Is it clear? So we observe a colored compound for the if incomplete d orbital, if it d orbital is completely empty or d orbital is completely filled, we will not observe any color for that. Shapes of the complex depending on the number of the ligands or number of dative bond. Like example, if it is forming a transition metal example, if it's forming 6 dative bonds, such as with water molecule or ammonia molecule, then the geometry will be octahedral. It is forming, if a transition metal is forming 4 dative bonds, then 2 possibilities are there. It can have a tetrahedral, or it can be a square planar. Square planar is valid normally for platinum. Others are not able to form the square planar. The geometry and the bond angle, you already learned these bond angles. Like in this case, each bond angle is 90 degrees. In tetrahedral, the bond angle is 109.5 degrees. And the square planar, the angle between, because like 2 of them are into the plane and 2 of them are out of the plane, and it will make a square with an angle of 90. So 90, 90, 90 and 90. And if 2 dative bonds are there, then it will form a linear structure with a bond angle of 180. So transition metal ion commonly form octahedral with a small ligand such as water and ammonia. Transition metal ion commonly form tetrahedral complex with a large ligands, such as if there are 4 and large ligands are there, it will form tetrahedral. Square planars are also formed. This cisplatin and transplatin, you will learn the next slide. It's there, the difference. Commonly they form tetrahedral and rarely they form square planar. But the platinum, when it attach 4 ligands or 4 dative bond it will form a square planar. And if it is forming only 2 dative bonds, then it will be a linear. So you can see here the dative bond, it's always even, like 2, 4, 6. It cannot, like you cannot have a one dative bond only, you cannot have 3 dative bond in a transition element. You will always have an even number 2, 4, 6. So copy this, then the shapes of the complex sign. There is a reason why some of them can form square planar and with the 4, some of them can form tetrahedral, but that reason you don't have to learn. In your course outline, you have to just remember that platinum can form a square planar and remaining others with a 4 coordination number of 4 or 4 ligands will always form tetrahedral. C and D, we observe C is a heavy. So if heavy groups are on the same side, what we'll use the word? We'll use the word cis. But heavy groups are on the opposite side, then we will use the word trans. So in this geometry, in this case, how we'll identify? So if both of them are on the same side, like example, you can see here, chlorine, NH3 and NH3. These two chlorine are on the same side. It's not like in the carbon-carbon double bond. If the bonds are in identical plane, that this dash line is representing that it is out, and wedge is representing it is in. So one is in, another one is out. So in cis and trans for organic compound, when they're in the same plane, like if X and Y are in the same plane, we'll use the word cis. But in these, it is a bit opposite. If the groups are on the same side, of same ligands are attached, so what we will call that as cis. But if opposite ligands are attached, like example NH3 and Cl, so this is heavy. When you check NH3 and Cl, so the groups, the comparison is between these two. Like in the same plane, we'll compare. We are comparing NH3 with Cl, so Cl is heavy. Then we compare another plane, like the plane in which there is out. So Cl with NH3, Cl is heavy. So both cases, the heavy groups are on the same side. What we will call that as cis. But when you check other way around, Cl is heavy. In this case, Cl is heavy. So when you divide this, they are on the opposite side. So when they are on the opposite side, what we call that as trans. But here, when I draw the line, the same heavy groups are on the same side. I will call that as cis. So cisplatin or transplatin, these are the two complex which are formed by platinum. Then platinum 2 complex, cisplatin is used as an anti-cancer drug. So basically what happened in the body, one of the chloride ligand is substituted by water molecule. And this is how it works. You don't have to learn that. You just have to draw the structure of cisplatin and transplatin. So draw the structure for cisplatin and transplatin. You don't have, and copy this part only. And the equation. So variable oxidation state for the transition element. So as the transition element, they show variable oxidation state. As they can form or they have variable oxidation state, so they are able to donate or receive different number of electrons, and they are able to oxidize and reduce. Like what is the reason? Like example, if you have iron 2, So if you have iron 2 can lose electron and it changes to iron 3, or iron 2 can gain electron and it changes to iron atom as well. So these elements can be oxidized, or their ions basically can be oxidized or reduced. Because the ions contain a partially filled suborbitals, so sometimes they can lose electrons, sometimes they can gain electron. So relative stability of +2 state with respect to +3 state increases across the period. So as we move across this period of these transition element, the +2 is more stable as compared to +3. And the compound with a high oxidation state tend to be oxidizing agent, like manganese is there. So Mn in MnO4 manganatine, the oxidation number of manganese is +7. So already it's +7, so it cannot further lose electron. It can gain electron. If substance can gain electron, reduction is gain electron, or the substance can be oxidizing agent, because the substance which is reduced, reduction occur, it's an oxidizing agent. Same thing, compound with low oxidation state, they are often, or they are more commonly reducing agent, because reduction is a oxidation is a loss of electron, or the substance will be an reducing agent. Like iron 2 is there. So iron 2 can lose electron and change into iron 3 easily, compared to iron 2 will change into iron atom. So the general trends, the stability of +2 oxidation state with respect to +3, it increases across the period. The compound of high oxidation state tend to be an oxidizing agent because they tend to gain electron or they reduce. And the compound with low oxidation state tend to be reducing agent, or they tend to lose electron. That's why they are reducing agents. Copy this one. So a substance which alter the rate of reaction, we normally call that as a catalyst. The catalyst normally provide an alternative route with a lower activation energy, and most of the transition element or their compound can be used as a catalyst. A catalyst can be a heterogeneous catalyst. A heterogeneous catalyst means it will have a different phase as the reactant, and homogeneous catalyst will have the same phase as the reactant. So how it works, these catalysts work, the main definition, and heterogeneous and homogeneous you will learn in detail. So here heterogeneous catalysts are usually solid, and where reactant are either a gaseous or solution, and the reaction occur at the surface of the catalyst. Normally what happens, like example, if nitrogen is reacting with hydrogen and forming a product ammonia, the reaction is reversible, ammonia can decompose back. So basically what happened, say we use iron as a catalyst in a Haber's process. So this piece of iron, the metal, they have interstitial spaces, means there are spaces between the ions. So these spaces will trap the reactant molecule, like hydrogen molecule are trapped on the surface. What is the advantage of trapping these molecules? So when it will trap these molecules, like example, these are the two hydrogen atoms and they are linked by a covalent bond between them. So this bond is weakened by the attraction of the positive ion, because there are a positive ion attract the shared pair. So due to this attraction of positive ion, and positive ions are, because they have more or greater number of electrons, so they trap and they attract the shared pair of electrons. So as they attract the shared pair of electron, this bond will become weaker, and nitrogen can easily break the bond compared to when hydrogen was there without a catalyst. So heterogeneous catalysts, which are usually solid, and the reactants are in a gaseous or in a solution form. So the reaction occur at the surface. As the reaction occur at the surface, So they absorb the reactant. First they absorb the reactant, then they reduce the bond strength so that it can break easily. So the strength of absorption help determine the effectiveness of the catalyst, because if it is, so the metal example W have too strong absorption, so the product cannot be released. So metal such as like here it's a tungsten, silver, which is having too weak absorption, reactant do not absorb so high, you need a high concentration. But nickel and platinum have about the right strength and more useful catalyst. Because when we are selecting a catalyst, if we select a catalyst, we have to check the absorption power of the catalyst. If absorption power of the catalyst is too high, then it will not allow this, maybe a reaction occur, but it will not allow this product, when the product form can be released, because attraction is too strong. Or if it is attraction or absorption is too weak, then we need a greater concentration of a reactant to carry out a reaction. So normally nickel and platinum have the right strength, so they are the most useful as a catalyst. Then the second thing, the surface area, increasing a surface area of solid catalyst will improve the effectiveness and support the medium in often to maximize the surface area and minimize the cost. So ceramic support in a catalyst. So normally what happens, if you want to be, a catalyst to be effective, so catalyst will be effective when they have a large surface area. So we can increase the surface area of solid catalyst, will improve its effectiveness and support the support medium is often used to maximize the surface area. What is the support medium, like example, and minimize the cost? If I say, like example, if I'm using a metal and the pure metal here is used as a catalyst. So if I'm increasing a surface area, I have to use greater amount of that metal, so it will increase the cost of the reaction. So normally what we do, we use a support material. How we use a support material? Basically, only the surface is made up of the metal, and below part, the part which is under, is not made up of metal. So the part which is under is called a support material. Is it clear?
Yeah.
So write about heterogeneous catalyst first. What is heterogeneous catalyst? And then the next slide you will copy the strength of absorption and strength of, and then how it, first I will explain this and then you can copy, or 5 minutes are there so you can copy. Heterogeneous catalyst, first write the definition for heterogeneous catalyst. They are usually in a different state as the reactant, and then the absorption strength and the surface area. Strength of absorption and surface area.